Okay, wrapping up the name graphs. First thing I want to do is backtrack. It was driving me crazy why on my graph I couldn't get that to show that the pedal length is 6. Um, and that's because I was stretching out the x-axis. I wanted the y-axis stretched out so you could count up from the pole. You can see that pedal length from the pole straight up is 6. So it was the y that I was mistakenly putting in the x, and sorry about that. All right, back to the lemniscate. So last video we talked about just that these are going to be figure eights. They're a little bit more complicated, for sure, but they're equations. Question might be first, how would I enter that in? How would I do this on a calculator? Well, your calculator won't accept r squared. It can only accept r. So we have to do or introduce a little bit of algebra and simply square root both sides of this equation. So, for example, if I said, I need you to graph r squared equals, let's make this good, about 25, let's go sine of 2 theta. Right? I want to graph this on the calculator. Well, first things first, I cannot enter in r squared equals this as is. What I have to do is I have to square root both sides. Now, the problem is when you square root both sides of an equation, you know there's a plus and a minus aspect to it. So this will be plus or minus the square root of 25 sine of 2 theta. Now, we're not going to do any fancy math to this. In fact, we can punch this in exactly as we see it. We would make R1 positive and the second one, R2, negative square root, and that will give me both pieces of this infinity symbol, and it should look like this one going sideways because it's a sine. The cosine lays flat, looks exactly like an infinity symbol. So we have to graph both the positive and the negative version, but we can simplify this a little bit because this is multiplication. We can square root these individually and say, well, that's plus or minus the square root of 25 times the square root of sine 2 theta. I mean, if you really want to do this, it's totally unnecessary if we're just going to see what it looks like on the calculator. And not sure this is necessarily any easier, but it should be the same thing. So plus or minus 5 square root sine of 2 theta. All right, hopefully my viewing window is still good. So let me put these both in and show you what it looks like just to make doubly sure we got this. Sine 2 theta. Negative 5 sine square root, forgot that, 2 theta. More I think about this, thinking I didn't save myself any time by doing that, square root of 25. All right, so that's what I have in. One's positive, the R2, the second one is negative. I'm going to graph both of those. All right, so we go to graph. We do get a very slow figure 8 because I don't think I changed my theta step from where it was. There's one piece. And slowly, there is the second piece. All right, my theta step, if I go back to my window, it's still going. Now, if you ever want to stop the graph like enough, what it's doing is it's tracing over itself right now. Just hit on and it should break the graph. It should break this, stop graphing is what I'm trying to say there. But let me go to my window, and I did, if you can see, a theta step of 2. Now, if I go back to my 15, I think I will still get a decent picture. And you notice it graphs much faster and done. What it's doing while it's still graphing is like it's not showing anything. It's just tracing on itself. It's actually going through that infinity loop twice is what's really happening with this graph. All right, so you get that infinity symbol, and you want a better picture of it. Again, you could do a zoom square, that number 5 choice on the zoom menu, and you'll see a better version of it. And if the theta step is too large, it will start making sharp points at these that should be nice, smooth, rounded curves there. All right, so these are a little bit more complicated. Now, if we go back to this, it's hard to see on this sine graph how long those, if you want to call them petals, I've really hesitant saying that word, but we'll call them petals for right now. If you look at the petal length, it's hard to tell when it's going diagonal. So let's change the sign to a cosine. So just go back and just put your cursor right at the sign and then hit cosine. It'll override it. I don't know how much I should say if it's being too elementary here, but there you go. Let's graph this. It should be an infinity symbol on its side. And again, it's still graphing because it's tracing over it. All right, so we get the infinity symbol on the side, and if you take a look at each, again, in quotes, petal length, they're exactly 5 units long, which is no coincidence here. We can look at that, or you can look at the fact that that number that we're writing here is a squared, where the a, the absolute value of a, I should say, but it's going to be a positive value. The absolute value of a will be the length of each petal. So there's your lemniscate. All right, last one. This is one we're going to need to put our calculator into radian mode just because of the large values we're going to get here. Right? The sine and the cosine in the other problems really calmed the numbers down and kept your ratios between -1 and 1, because that's what sine and cosine do. Their range is from 1 to -1, so that you're not going to get massive values. Well, here, if you don't have sine and cosine in your equation, well, you're going to have to go to something that's not so massive. Right? Now, we could do it in degrees, but radians are going to be a little bit easier. All right, so number 7, very fancy name. It's called the spiral of Archimedes. I'm always afraid I misspell that. The spiral of Archimedes. Right? And just like the name implies, a spiral of Archimedes will start at the pole, and it will spiral. Not once, not twice, not 3 times, but it keeps spiraling out to infinity, depending on, how big your theta max is. If you just go 0 to 360, well, it's only going to spiral until the calculator gets to 360. You go 0 to 720, well, it's going to keep spiraling until you get to 720. Right? So however big you want the spiral, it depends on your theta max. Right? So the equation is actually very, very simple. It's r equals n times theta, some integer times theta. Now, again, I can only vouch for when n is some sort of integer, non-zero integer again. So n is a non-zero integer. If n is positive, it's going to spiral counterclockwise. If n is negative, it's going to spiral clockwise. You don't want to pick too large of an n value. I'm going to actually stick with n equals 1 just to make things simpler. Because the larger this n is, the more window you're going to need. You're going to have to really alter your x-min, x-max, y-min, y-max to see this spiral. Right? So let's try the simplest of all. Let's just graph r equals theta. Right? So the n value here is 1. That's what I'm choosing. So this thing is going to spiral counterclockwise. At least it should. All right, first things first, go to mode. We're going to have to change our mode here for sure. Like I said, let's go to radian mode. All right, let's go back to this, clear these two guys out. And all we have to do is, simple as it gets, r equals theta. All right, now, if I just hit graph right now, let's find out what it does. Just see in the viewing window I have. Okay, that looks absolutely terrible. Why did that look so terrible? It looks terrible because you're going from 0 to 360 radians, right? So we have to talk in terms of degrees. So 0 to, let's just go 2 pi. Now, I hit in, whoops, that's my, let's go 0 to pi. Now, I put in 2 pi. Now, once I go and off this right there, it'll convert it to 6.28, whatever 2 times pi is. Now, theta step, you don't want to go by 15. You're already past your maximum. So what I'm going to do is, let's just do pi divided by 10. Right? So pi tenths, just to be weird. You can go pi 20ths. I mean, if you don't want to think in terms of pi, just go, let's go 0.1, whatever. It's not that big of a deal. You're going from 0 to 6.28, whatever. Let's count by 0.1s. That should be good. All right, now I don't know about my window, X-min, X-max. Let's just graph it and find out. And there you go. It has finished. So I'm going to need to zoom. If you hit that zoom button and just zoom out. Now, what it's going to do is it's going to take you back to your graph. It's not going to zoom out for you right away. It puts that cursor somewhere. I like to put it right at the pole. So move your cursor to the pole. So like that. And just hit enter and it's going to zoom out. What do we get? Well, that's underwhelming. So we want this to spiral more than just once around, right? So instead of 0 to 2 pi, go back to your window and let's go 0 to about 10 pi. So just type in 10 pi, like that, and let's see what it does now. Should spiral a little bit more. There it goes, spiraling out till the calculator gets to 10 pi, eventually to 10 pi. Are you getting to 10 pi? There, I think it made it. All right, so that's the kind of graph you're going to get. And if you put in a negative, like if we were to graph negative theta, I said that's just going to spiral clockwise. That's all the negative in front does. So now we're spiraling. Actually, that's counterclockwise. It's the same direction. What did I just do there? Negative theta. Negative theta. Graph. No, still spiraling counterclockwise. Thought the negative would make it spiral the opposite way. I'm starting to think, which way did the other one spiral? I think it was both counterclockwise. In any event, you do get a spiral. And last thing I want to say is if you go to zoom and square it out, you'll get a truer picture of the spiral. So what the zoom square does is it makes it look more true. And that's actually what it looks like. Now the spiral is still keeping that same width going all the way through it. So kind of neat. And if you kept going, it would, spiral out to infinity, just keep getting larger and larger, but keeping that same width in between each spiral. All right, that should get us to the next video where we're actually going to graph some of these things.